Hey guys, welcome to part 2 of neural networks from scratch in C++. In the last video, we discussed how we can convert a simple linear equation into a neural network. And then we showed how we can represent it very compactly using vectors, which we introduced as well in the last video. Now I want to extend this language of vectors to something that is, it's not that much more difficult than vectors. We're going to be looking at these objects called matrices. So I'm just going to draw over here. So matrix in the singular. And really these matrices are just extensions of vectors. So they do pretty much what vectors do, except they're a bit more powerful, and they're typically treated in a different fashion. So a matrix, you can think of it as, so I'm going to use this bracket notation. So I'm just going to make an arbitrary matrix. So similar to how you had a single list of numbers for a vector. Actually, let me just make this ordered. So 0, 1, 2. A matrix, now you have, you can think of it as having multiple rows and multiple columns. So in this case, I made a 3 by 3 matrix. So when I say 3 by 3, typically you start with the number of rows. So I have 3 rows and 3 columns. So I have a 3 by 3 matrix. And there are two very important representations that you need to be aware of when we're talking about matrices. So you can think of a matrix as either a vector of row vectors. So that's a bit complicated, but let me explain what I mean. So let me highlight a row. Okay, so here you can think of this as a vector, right? So remember we talked about how there are column vectors and there are row vectors, and row vectors are just on their sides. So let's say that I had the vector 0, 1, 2. And let me make another vector for 3, 4, 5. I'm just going to call this x, 3, 4, 5. And I'm going to make another vector. I'm going to call it y. And this vector is 6, 7, 8. So this matrix, matrices typically you denote with a capital letter, and I'm going to put a capital A. And you're going to see that I'm not putting a vector symbol like the arrow on top. Typically matrices, they don't have that. But you can still think of A as a special type of vector. So instead of representing it as expanding the numbers directly, I could have written this as a vector that stores v, x, and y. So this is the row vector representation of a matrix. You might wonder, why is this important? Just follow along for now. It'll become clear very soon. So this is one representation. The other representation is to look at this as a vector of column vectors. So if I were to have drawn a rectangle around this column instead, and I make vectors for every single column, so I'm not going to do it explicitly this time, but I'm going to make 3 vectors. So A, I'm going to just do it for the first one. So 0, 3, 6. So this is one vector. And then I could have B. I'm not going to fill it in, but this B is 1, 4, 7, and another vector C, which would be the 2, 5, 8. So another representation for A would be a row vector that holds on to these column vectors. So A B, and C. So imagine if I were to expand A out, it would form 0, 3, 6, and that's what you kind of have to think of in when you're thinking of these representations. You expand it, and it expands to this 0, 3, 6, and then the B expands to 1, 4, 7, and C expands to 2, 5, 8. And the same idea for when you have the column vector of row vectors. The V here expands to 0, 1, 2, and then X, 3, 4, 5, and Y, 6, 7, 8. Okay, so there are two different representations. So this is the row vector representation, and this is the column vector representation. Okay, so now there's a special way that we do that we can think of matrix multiplication. So I'm going to make, well, I'm just going to rewrite this matrix because it got a bit messy on the left. So I'm going to, I think it was, yeah, just 0, 1, 2, 3, 4, 5, and 6, 7, 8. So this was our matrix. Now I'm going to make another matrix for, actually I'm just going to continue, 0, 1, what am I saying? I'm continuing, I'm not copying. So 9, 10, 11, 12, 13, 14, 15, 16, 17. The numbers got a bit big, but that's no problem. So let's say we wanted to do, well, it's kind of unmotivated, but I want to do matrix multiplication. So I want to show you how we define matrix multiplication. So to do that, we do, to represent the matrix multiplication, you just represent the matrices side by side. You don't put any operation symbol between them, just AB, for example. And it's inferred that we want to do a matrix multiplication, given that on the left we have a matrix, on the B we have a matrix. So how do we do matrix multiplication? Well, the way that we do it is we essentially need to represent the first matrix in row major representation. So the way that we think of A is as, like, imagine, as we just discussed, a vector of rows. So we have 0, 1, 2 is a row, 3, 4, 5 is a row, and 6, 7, 8 is a row. And B we represent in column major representation. So I'm going to highlight the columns. And really, what matrix multiplication is about, or what it tries to achieve, is it's trying to store the results of all of the possible dot products that we can have between these two matrices. That's all a matrix multiplication is. So remember, we discussed how a dot product, if I have it over here, for dot products you multiply term by term and then you accumulate the final results into like one final result, right? So in this case, 1 times 4 is a partial, 2 times 5 is a partial, 3 times 6 is a partial, and you accumulate the results. So we looked at dot products as dot products between just these column vectors. But there's a, typically, the way that you do a dot product without having to actually put the dot symbol in between is you need a row vector on the left. So for example, V, if we want it to be a row vector, so this column vector 1, 2, 3, to convert it to a row vector, we put a big capital T at the top. And this capital T is the transpose operator. And what it does is it flips 1, 2, 3 on the side so that it ends up being a row vector that looks like the following. 1, 2, 3. And V dot G, another way to represent this, that arrow is not great, hopefully that's a bit better. We can rewrite this as V transpose G. So you might be wondering, like, why? Why do we have to do this? Well, very similarly to in the matrix multiplication case, the left is always in row major representation and the right is column major representation. In dot products, we need the same thing. To actually, to compute the dot product, you can look at this as a type of matrix multiplication, okay? So I'm going to rewrite this as 1, 2, 3, and 4, 5, 6. So remember, I said matrix multiplication, you can think of it as all of the possible dot products that you can do. But in this case, the way that you do the dot product is instead of multiplying term by term as if they were both column vectors, you just look at the index in the row vector. So in this case, the first index 1, we have the value 1, and then we have the value 4 in the first position of the right vector. You multiply those and then just walk through and do the same thing for the other values. So 2 times 5, 10, 3 times 6, 18, and add the results up. I won't go into much detail now about why we require this, the left being in row major and the right being in column major. There's some nuance there. I could potentially get to that in further videos if anyone's interested, but for the time being, just take my word for it that that's what we have to do, and that's how matrix multiplication is defined. So a dot product is like a simple matrix multiplication in the sense that we're just doing it between two vectors. But if we go back to the matrix multiplication case, we have to do it between all possible pairs of vectors, where a pair is one vector or one row vector on the left and one column vector on the right. Okay, so I mentioned that the matrix multiplication stores all of the possible outputs we can get from this, but I don't want to think about that right now. I just want to think about, okay, well, how many dot products can we have? Okay, so this 0, 1, 2, we're saying we want all of the possible dot products that we can between vectors in the right matrix. So for this one row vector, it can be dotted with 3 possible column vectors. Okay, so that means that we would have 3 results per row vector. So for every row vector on the left, we would end up having as many column vectors as there are on the right results. Okay, so that means that let's say that well, in this case we have a 3 by 3, and we have a 3 by 3 as well here. So for this one row vector, we have 3 possible results. But now, how many row vectors are there on the left? Well, we have 3 row vectors, and for each one of these, we can get 3 possible results. So in total, we have 3 by 3 dot products. So we know that in our matrix multiplication, we're going to be doing this 9 times. So 3 by 3, well, 9. Okay, and every single dot product, well, how many multiplications are there? Well, there would be the length of this vector, that would be how many multiplications we have to do. So in this case, the length of the vector, or the number of elements in the vector, is 3. So we would end up having 3 by 3 dot products, but if we want to talk about the number of multiplications we would have, it's, well, we have 3 by 3 dot products, and for every dot product we have 3 multiplications. And then we have, well, 2 additions, but the multiplications are the expensive operation. So in total, we have 27 different multiplications that we're doing, or more specifically, 3 cubed. And in general, if we have a matrix of shape A by B, and we have another matrix, B by C, we're going to have A times B times C different multiplications that we're going to do. And now you might have noticed this. It's like I have an A by B, and I'm matrix multiplying it by B by C. Could this B be anything else? Could it be a different value? Like, does the number of rows in the right matrix have to be the number of columns in the left matrix? Yes. And it's very easy to show. I don't need to show it specifically for like a big case like matrix multiplication. But if I were to go back to the vectors, let's say I added an additional term to this vector. So I'm extending it by 1. Well, remember the dot product, we multiply term by term and then add up the partials. But there's nothing on the left that we can multiply by this 8. So therefore, for dot products, the vector lengths need to be equal. And that means in the matrix multiplication case, another way of saying that is that the number of columns on the left needs to match the number of rows on the right, because we are doing dot products with row vectors on the left with those and column vectors on the right. So we need this thing called the inner dimension. So this is the inner dimension. We need these to match. Okay, great. So now we have some intuition for matrix multiplication. In the next video, we're going to actually perform the matrix multiplication. See you there. All right, bye.